Getting into the shallow foundation section, there are 4 subtopics on this for this lecture. However, only 2 are actually specified on the exam. So the 2 that are specified on the exam are the ones not highlighted in red, and that'll be bearing capacity and settlement. So the other ones I've included for this section are vertical stress with increasing depth, and then eccentric loading and combined footings. So the reason I indicate these 2 is because when I took my exam, I distinctly remember there being a question on vertical stress, and I remember there was at least 2 on this topic right here. So I thought I would cover them for you just so you kind of had an idea of what to expect. So for approximate methods to estimate vertical stress, and I want to stress approximate methods, you can actually use one of these 2 equations. And so if this was a square here, what I would do is I'd have B plus C and L plus C, and so I'd have an area at this level below the surface. And so I would take this P and divide it by the area at this point here, and I would get a pressure. And you could say this is approximately what the pressure is. And conversely, some people don't like the 1 to 2, so they'll use a 60% angle here, and they think that gets a better approximation. However, once again, these are just approximate methods here. So one of the things I will stress is that one of the main reasons they're approximate, if you notice, the pressure distribution is uniform across the entire width down here. However, that is not the case. When you start talking about the stress below here at the corner and at the center, the stress at the center is actually definitely a lot higher than the stress here at the corner, and more so down here at this point right there. So the way the stress distribution actually appears is actually a bit parabolic. However, these are approximate. If you were saying I just need to figure out kind of if I'm in the ballpark, this is kind of close to get you there. When you start talking about getting a little bit more precise in terms of tailoring it down to that parabolic curve, you can start getting into the WMSS model, which this is a model that WMSS came up with in about 1887. And basically what he did was he said, if I have a point load here and I want to figure out the stress in this element down here at a distance x, y, and z away, I can use this equation to actually figure out what it is. And kind of what this equation really came up with was the idea that there's a certain radius that's affected by this point load, and this radius gets bigger as I go through here. So as the radius gets bigger, the pressure decreases. And so that's kind of what this is alluding to here. And so I can take this pressure with these distances here and actually calculate kind of what the change in pressure is due to this load. And so this change in pressure would be just increased or added to the effective stress when we actually get into some of the bearing capacity issues and settlement. So the WMSS model kind of went from that point load to be any point load there to say I have this foundation here, and this foundation is uniformly loaded, and it has a uniform pressure of Q naught. I can use this equation here with the influence factor to actually figure out what the pressure is below any corner at a distance z below the surface. So one of the other ways that you can use this model, and I'm probably not going to get into it too much during this lesson, is say I wanted to find the pressure outside of this point here, and so z was actually not below the actual corner. I could create some imaginary surfaces to get to that point, and then that'll give me the approximate pressure based on this diagram here. Once again, I'm not going to get into that. If you want to kind of read into that, you can look up in the CE reference manual. I just kind of want to get the basics out to you. And so this influence factor is actually calculated using all 5 of these equations right here, with this equation being the main one, and then these 4 actually adding into it with the different variables. And so M and N are basically just ratios of the width and the length over the actual depth of it, and then alpha is just ratios of the M and N products, and then when you plug it in, you actually wind up with an influence factor. And so this influence factor gets directly multiplied by Q naught to get the change in vertical stress or vertical pressure underneath the corner. So there are other methods out there. This is the WMSS stress contours. And so over here we have a square foundation. And so essentially what happened was they took some of the earlier WMSS work and then created contours for it. And so these are the two for infinitely long, i.e. strip footing, and square foundations. Subsequent stress contours have actually been created as well for circular, and I believe for rectangular as well. However, you'll have to try and find them. These are the only two I could find readily available, and I believe these two are actually in the CE reference manual and in the all-in-one handbook. So the way this would work is, say I have a square foundation of width B, and I want to figure out what the stress is 2 widths below the surface. I can come down here and say it's roughly 0.1 times Q naught, and basically come up with the change in vertical pressure is equal to this value. And so I'd multiply 0.1 times, say it was 1,000 PSF, and I'd wind up with 100 PSF increase right below the center at this point. If you want to do the corner, you would just come down here, or say I want to find a value 2B away from there, and I would come down here to 2B, and I could figure out 2B away and 2B down, and it would be 0.2. And so if you do notice, like I was saying, the pressure below the actual foundation at any given height or any given depth is parabolic. So if you notice, if I'm down here at the center, I'm at about 0.06 Q naught. However, if I start moving away, I get to 0.04, 0.02, 0.01, and then 0.005 Q naught. So just keep that in mind. That's kind of why the approximate methods are, as they're named, very approximate. They'll kind of give you an in the ballpark range, but when you use the stress contours, you're going to get a little bit better answer. So if you are going to have to calculate the vertical stress or due to a load on a soil, then I would probably use the stress contours if you can. There is one more method which you could potentially use this on the morning exam. However, I think this would be more of an afternoon topic, but I just wanted to at least show it to you. So this is called Newmark's chart, which Newmark kind of took a lot of what WMSS did and then just kind of created his own chart for it, so you can create any sort of foundation on here. So you can deal with irregular shapes, circles, any type of foundation you may have, and plot it on here to figure out what kind of stresses will be below that foundation. And so the way this works is I've drawn two squares on here, and so you would take the square down here and match it onto here, and so this unit is going to be equal to whatever depth you're trying to find. And so if I want to find a depth that's 20 feet below the surface, one unit is going to be 20 feet. And so what I would do is I would size my square based on that. And so if I had a 20 by 20 foundation, then this would be 1 unit by 1 unit. However, if it was 10 by 10, this would be half a unit by half a unit. And so you can kind of see where I'm getting at with this. And so the other way this is going to work, you notice I did draw two. These are two identical 1 unit by 1 unit squares. The main difference is this square right here is finding the stress below the center, and then this outer square here is finding the stress below this corner. And so the way this chart works is you would draw your shape, and you would put the center of the shape or the corner of the shape here in the center, depending on which one you're looking for. So if you're trying to find the stress below the center of the foundation, you would basically put the center right on the center. But however, if you're trying to find it at the corner, you would take this corner and put it on the center of the circle there. And so the next step in this process is to calculate N. And so say if I want to calculate this one, all I would have to do is count up the number of squares that are actually covered by this square. So the way you want to go about doing it is count all the full ones first and then start counting the partials. And typically the way you would do it is you'd add the partials together, try and make a full one. And as you can say, this, as you can probably tell already, this is very, very approximate in terms of one person may do this and count 67, someone may count 68, and someone may count 65. It just kind of depends, but generally you're going to be in the area. But as you can tell, depending on what you count, you're going to wind up with different values, because the equation is going to be equal to the influence, which is 0.005, which is always written at the bottom of the chart, times the original pressure at the surface, times the number of squares you count, and that'll equal the change in pressure. So kind of an example problem I wanted to show you just to kind of give you an idea of how this is actually done. So if I have a 20 by 20 foundation and I want to find the pressure 20 feet below the surface or below the center of this, how would I do it? And so the first one I'm going to do is look at the WMSS contour charts. And so I would just pull out this square foundation here. I've kind of blown it up to make it a little bit easier for you. So directly below B and at a distance B below the surface, this is actually about 0.33. It's kind of hard to see because this chart has the 0.4 covering it, but 0.4 is a little bit higher than this, and so I kind of estimated it was about 0.33. And so multiplying 0.33 times 5,000, I'll get 1650 pounds per square foot at this point right here. If I use Newmark's chart, I'm going to wind up counting about 68 squares, making a 1 by 1 square and placing it over there. And so that 0.005 influence times 5,000 times 68 gives me about 1,700 pounds per square foot. And so if I compare that to the approximate methods and the WMSS model, you're going to wind up with about 1,650, 1,700 for these two indicators, and about 1,250 and 1,077 for these two. The reason the WMSS model wasn't calculated is because WMSS is for the corners, and since I calculated the center, I couldn't use it. I had to use Newmark's or the stress contours. But as I kind of alluded to earlier, when you use the approximate methods include a uniform pressure at the depth of interest. However, when we were calculating at the center point at that depth, we have to remember the approximate methods don't account for that parabolic shape that's down there. And so the pressure on the corner will probably be a lot closer to these ones. However, the pressure in the center is closer to 1,650, 1,700 roughly. So now getting into bearing capacity, there's three types of bearing capacity failures. We have a general shear failure, a local shear failure, and a punching shear failure. So most of the bearing capacity equations we're going to be looking at will generally all evaluate for general shear failure. And the kind of the thought is when they've evaluated for this and they've designed for this, it'll basically count for the other two. There's some merits to that. However, they generally consider this to be the primary mode of failure for these. The punching shear failure basically assumes that this is just going to fail straight down through the surface, as in the surface will not be able to hold it anymore. This is pretty rare in terms of happening, so I would tend to agree with most people that this is going to be your primary source of failure. And so when you look at the bearing capacity failures, if you ever get a conceptual question, which type of failure are they targeting, it'll generally... The first method we're going to talk about to calculate the ultimate bearing capacity for shallow foundations is the Terzaghi method. So for shallow foundations, we're generally looking at the depth being less than or equal to the width. And this is pretty much the primary assumption that you need for the Terzaghi method. If this isn't true, you have to go into basically the Meyerhof method, and I'll get into that in just a few minutes. But the Terzaghi method varies depending on which foundation you're actually looking at. If you're looking at a strip footing, a square foundation, or circular foundation, you have to use a different equation. And so the only things that really change are these coefficients, basically in front of the cohesion factor, and then in front of the self-weight factor. So if I look at the square foundation, this 1.3 times cohesion times the cohesion factor, this is basically looking at the actual soil properties, the cohesiveness of the soil. Then we get into the surcharge factor, which is depth of the foundation and the unit weight. And so then we get into the actual self-weight factor, which is the width of the foundation times unit weight, and then times our self-weight factor. And so these are the three factors that go in to actually determine the ultimate bearing capacity of the soil. And so Terzaghi's bearing capacity factors depend on the internal friction angle. And on the next slide, I'll show you what they actually look like. However, as I said earlier, this applies to the general shear failure mode. If you want to calculate for the local shear failure, Terzaghi has some modified bearing capacity factors that you can use to actually calculate it. So these are the bearing capacity factors for the cohesion factor, the surcharge factor, and the self-weight factor. And so as you can kind of see, as the internal friction angle increases, the cohesion factor will increase as well as the surcharge factor and the self-weight factor. So just keep this in mind. Depending on which internal friction angle you're using, you're going to wind up with some different factors. So make sure you're keeping that straight. especially if there's ever an equation or an issue where it talks about a change to this value or what have you. But getting into the Meyerhof factor, which is basically applicable to any shape of foundation for shallow and deep, as you can see, this equation gets a lot more cumbersome. And so basically what we have is a lot of the shape modification factors, which are these values right here with the S's in front of them, or at the end of them rather. And then we have a depth factor, which is the D, and then we have an inclination factor, i.e. if there's an incline near the surface, or even if the foundation is a little bit inclined, you can use these factors to account for it. Otherwise, these will basically be 1 for most every case. The ones that you'll primarily be dealing with, if you have to use the Meyerhof one, will be the shape and depth factors, which, if you look in the CE reference manual, there's an explanation of what the values are. And typically, if you're going to use a square or you're going to use a circle, then what you're going to wind up having is the values be 1 or 0 or something of that nature. And so you can just plug it in relatively straightforward and easy. But you'll wind up using these modified bearing capacity factors and just be able to solve for the ultimate bearing capacity. One of the things to keep in mind when you're calculating the ultimate bearing capacity is the location of the water table will severely affect your results. And so if I look at case 1, where the water table is actually above the depth of the foundation, then we have to modify this factor right here, and we have to modify this factor as well. And so the way we would have to modify it is we would have to use our effective stress. And so getting into this first term right there, I would have to calculate the effective stress down here at the bottom. And so I would have to use this one as unsaturated and this one as saturated. And so that would have to be this stress here plus this stress would have to go into this term right there. And so if I start looking at this other one over here, when I start calculating this term there, it's a very similar issue in terms of using the effective stress instead of just using the unit weight. Getting into case 2 only affects this term right here. So you would plug in the y average or y bar into this equation, and that would basically fix your ultimate bearing stress. This term would remain unchanged as because the water table is down here, it's not affecting this depth here. And so this pressure right here will still be accounted for with this term. And then case 3, we basically assume the effective stress is equal to the unit weight, which is basically implying that the depth of the water table is so low that it's significantly lower than the width of the actual foundation if we were to plot that vertically. So just something to keep in mind if you are calculating the ultimate bearing capacity and you see water table thrown in there, you're probably going to have to consider one of these. Hopefully it's case 3 or potentially case 1. Case 2 isn't that much harder, it's just the equation's a little bit more cumbersome. So talking about consolidation settlement, so this is what I alluded to earlier when we were initially talking about consolidation, is the elastic settlement piece of it. So what I want to do is evaluate the consolidation settlement for this situation. And so without the load on it, the water table is 8 feet below the surface. And as soon as I add my load to it, 3,000 psf, it suddenly decreases the water table 4 feet, and so we have it 12 feet below the surface now. And so I want to figure out what the actual consolidation settlement is of this clay layer. And so the first thing I want to do is calculate the actual stress right here in the center of the clay layer. And so to calculate that, I'll do 120 pounds per cubic foot times 8 feet. And then I'm going to go ahead and add that to 135 minus the water pressure and multiply that by 4 feet. And then I'm going to come down here and do the same thing with the clay layer. So I'll do 110 minus 62.4 times 6 feet because I'm interested in what the pressure here is in the middle of the clay layer. And so I'm going to wind up with 1,536 pounds per square foot. So now adding that load and shifting the water table down, one thing I will say is I'm going to assume for this problem that the foundation is sufficiently large, i.e. I'm going to assume that the foundation is somewhere in the magnitude of 100 by 100, because what that'll basically allow me to do is 100 by 100 foundation at 12 feet below the surface. You can roughly say that this pressure is going to be the same as it would be down here. And so with a sufficiently large foundation, because of the pressures involved and the actual dimensions, if you remember back to my stress contour chart, you can kind of see with whatever the width is, the width or the pressure is determined by the width below the surface. And so if it's 100 by 100 and we're only talking 18 feet, obviously the change in vertical stress or vertical pressure down here is basically minimalized significantly. So you could basically assume this is 3,000 psf. And so what I'm doing here is I'm adding the 3,000 psf directly in. And so I'll have 120 pounds per cubic foot times 12 feet, because this is above the water table. So I can just take 120, multiply it directly by 12. And then I'm going to have 115 minus 62.4 times 6 feet, which gets me at the middle. And so that'll equal 4,700 and about 56 pounds per square foot. So getting into actually calculating the change in the void ratio, we're going to wind up using this equation right here. And so I'll plug in my coefficient of consolidation, which is 0.35, and I'll multiply it by the log of 4756 divided by 1536, and I'm going to wind up with about 0.1718, which is a pretty considerable change in void ratio. And so if I want to actually convert that into an actual settlement, so I know how much that really comes down to, if I multiply 12 feet times that change and divided by 1 plus the original void ratio, I'm going to wind up with about 13 inches. And so that's 13 inches of settlement that happens during the elastic portion of it. And that's really without even getting into the consolidation of this. And so with consolidation, this will decrease even more. So now talking about eccentric loading, this is something I remember at least having 2 questions like this on my exam. So I wanted to bring it to your attention so we could actually start talking about this so you'll be prepared for it. And so talking about what I was talking about during the structural lesson was the current point. And so the current point kind of dictates whether we have a uniform load here, or we have, all compression, or we have some tension involved. And if something is within the current point, you can assume it's going to be all tension or all compression. However, once you get outside the current point, and when you have this compressive force, there's going to be some uplift. And that's kind of what this is indicating. So with zero eccentricity, we have a uniform pressure. However, if the eccentricity is within the current point but not on the edge, we're going to have a shape that looks like this for the pressure distribution. But once we get to the edge of the current point, then we're going to have essentially a zero stress or zero pressure here, and then we're going to have all compression right there. But as soon as I leave the current point and E becomes greater than B over 6, then suddenly I'm going to have some uplift on this end. And so depending on what the eccentricity is, we're going to have to account for it. And so we're going to wind up using this equation right here to actually figure out what the max and min compressive stresses are. So this equation is what you'll be using when you actually have to deal with eccentricity, especially on a footing like this. And so getting into combined footings, and the question I have for you right now is what value of B will allow uniform pressure under the footing? And so the way we're going to calculate this is by determining the resultant force and then figuring out where the resultant force is. And since I know uniform pressure means the force had to be applied at the mid-width, or exactly half of the width, then I can figure out, depending on where this resultant is, I can multiply that by 2 and then subtract off 6 to get the actual width we need, or the actual B. So to solve for this, what we're going to do is take the moments about the column A. And I'm going to go ahead and call this column A right here for reference. So what we're going to do is, as we're taking this, I'm going to go ahead and take this negative 80 foot kips and this negative 100 foot kips moments and plug those into the equation, as well as this negative 85 times 4 feet moment. And then I'm going to add a resultant at some x bar distance away. And so that'll be our moment equation. So if I solve for the x bar, then I'm going to wind up getting a value of 3.852 feet from this column. And so from the center line, that places it roughly right over here. somewhere probably within this column. And so if I was to take that from the left side, it would be 2 plus 3.852, which would give me about 5.85. So still, once again, about right here. So one thing I will say, I did kind of skip a step here. So the resultant has to be 50 plus 85, and so I just went ahead and threw that in there. So if you're trying to follow along with me, that's where the R came from. And so just solving this for x, you wind up with this value. And so to solve for the uniform pressure, I went ahead and placed our resultant right here. And so we know that's going to be 5.852 feet from the left end, and that's at 3.852 plus 2 feet. And so all I need to do is multiply this by 2 and then subtract 6. And so when you do that, you wind up with 5.704 feet. And so if this is 5.704, you're going to wind up with uniform pressure.